In this video, we're going to talk about the fundamental theorem of calculus. This is section 5.4 for Math 141. One of the things that should be known by now is that computing definite integrals by taking the limit of Riemann sums can be really difficult, right? And so you guys should have seen an example where we've done this, right? That's the limit as n approaches infinity of our Riemann sum, right? Well, it's the Riemann sum, right? It's k equals 1 to n of f sub xk times delta x, right? And there's an n here, right? That limit can be really, really difficult to calculate, right? And so remember, we said that that limit is the exact same thing as the integral from a to b of f of x dx, right? And so this f of x is the same thing as this f of x here, and this dx kind of is represented there, right? And so remember, we do the limit of this sum here as our Riemann sum gives us the area. If you think about it geometrically, the area under the curve, we calculate that area by adding up a bunch of the angles, right? And so the area should equal that integral there, right? And so we said that this limit was the same exact thing as this definite integral. And so if this is hard to do, but it equals this thing here, maybe we can spend some time focusing on that definite integral in order to help us calculate instead of having to do the Riemann sums. This is almost identical to what we did with derivatives, right? We said that the definition of a derivative of a function was the limit f of x plus h minus f of x all over h, right? We said that that was the same thing as f prime of x. So we started calculating these things by looking at these limits and how we evaluate those limits. And then we learned a bunch of rules to get the derivative, which is that f prime, right? That's exactly what we're going to do here, right? Anytime we see a definite integral, we should be thinking about this limit right here sitting in the background. What we're going to do for the rest of the course is look at methods that will help us to come up with how we can calculate this definite integral here, okay? And one tool that helps us get there is the fundamental theorem of calculus. There are actually two parts to this theorem. We're going to discuss part one now. Basically says if f is a function that is continuous on the interval from a to b, right? So if I drew a picture, I'll have me a function f that is continuous on a to b. Then it says then capital F of x, which is the definite integral from a to x. Now, you should notice something here. This is a function of x. This is our antiderivative, right? Because it comes from an integral, right? And this is the variable x here. Okay, notice that there. Now, this f that I have that I know is continuous on a to b is actually the integrand here, right? And so when I draw the graph of f, little f, so let's draw a continuous function, right? It is a function of t, f of t. So that means my x-axis is a t-axis, and my y-axis, I'm just going to let that be y, right? This function is continuous. I'm going to let a to b be here. It says capital F of x equals the integral from a to x of f of t dt. All right, so this is a definite integral because it has limits of integration. Remember, the definite integral kind of gives you the area under the curve, right? It equals your Riemann sum. But this right endpoint is x. And so x is a value of t that's in this interval here. All right, x may be here, x may be there, x may be there, x may be there. X is a variable that can take on any of these values between a and b. All right, and so what this capital F of x is basically a function that models the area under this curve, right? So if x is at this endpoint here, I'm going to call it x1. Then capital F of x, sorry, this is kind of getting out of the bounds here. This area is capital F of x, right? Now, since x is a variable and it can be any value from a to b, f of x is basically a bunch of areas here, all right? It's saying that this function that represents these possible areas from a to b is continuous on a to b and differentiable on the open interval from a to b, and its derivative is given by the following. this equals f of x. The derivative of this integral from a to x of f of t dt is f evaluated at x. And so this, in other words, the derivative of the integral is the integrand. So if I do the derivative of an integral, right, and as long as my integral goes from a to x, it is my integrand evaluated at that value x. And so what we're going to do is we're going to look at some examples where we find these derivatives. So example 1 says, use the fundamental theorem to find dy dx, right? I have y equals the integral from a to x of t cubed plus 1 dt, right? So this is my little f of t. That's a continuous function on an interval that starts with a and is going to end at b. This is actually continuous for all real numbers. And basically, I want to find dy dx. Well, based off of the fundamental theorem of calculus, dy dx is going to equal my integrand evaluated at x, right? And so I'm just going to, everywhere I see a t, I'm going to replace that with x, and I get x cubed plus 1. And this follows straight from the fundamental theorem. Okay, the derivative, since this is an integral, a definite integral from a to x, if I want to know the derivative of this y with respect to x, I evaluate my integrand at x. Let's go to part B here. Here I have the integral from y equals the integral from x to 5 of 3t times the sine of t dt. All right. Now, this is different from my fundamental theorem because it has the integral from a to x. So some value on an interval, right? So this is a value, and this is my variable x. Well, this has x to my value, right? Well, we can use that property of definite integrals that, oh, I can switch the order of my limits of integration by negating my integral, right? And so this is the negative of the integral from 5 to x of 3t sine of t dt. Now that I have it written in that form, I can find a derivative of this integral that's a function of x. And so that means dy dx is going to equal negative 3x times the sine of x. All right. And so if it's not written with the constant as your lower limit of integration and your variable that you're differentiating with respect to, so we're doing the y dx, as your upper limit of integration, you switch that order and you use that property from integrals. And so this is what dy dx equals for this example. Isn't that cool? All right, let's go to part C. It says y equals the integral from 1 to x squared of cosine of t dt. Well, notice when we go to our fundamental theorem, our fundamental theorem has just an x here. What do we see in part C? Going too far. We see a function of x, all right? So this is a function of x, all right? So the fundamental theorem doesn't apply exactly for this example. So what we're gonna do is we're gonna use what we call a U substitution. This is almost like using our fundamental theorem, but like with a chain rule, okay? So what I'm gonna do is I'm gonna find a variable u. I'm gonna call it u, and I'm gonna let that equal x squared, right? And so at this point, I'm basically writing y as a function of u instead of as a function of x. I'm gonna say this is the integral from 1 to u of cosine of t, that should be an s, cosine of t dt. Okay. So again, since that wasn't just an x there, that's an x squared, it's a function of x. What I'm going to do is replace x squared with u, and now I have this as a function of a single variable, right? Now, my goal is to find dy dx. But this thing has y as a function of u, which is a function of x. All right, so kind of think about composition of functions, right? I start with an x, I apply it and I get a u, and from that u, I get y, right? Because y is a function of u, and then that's a function of x, right? And so when I do my derivative, this is going to be a dy over du, but since that u is a function of x, by the chain rule, I have to multiply it by du over dx. And so when I do this derivative, it is going to be from my fundamental theorem. I'm going to come under here. dy du is basically cosine of u, but I've got to multiply that by du dx. Okay? Now I'm going to rewrite everything in terms of x. So since cosine of u was equal to x squared, so I'm going to go and I'm going to replace this x squared for u here. Okay? And since I know that u equals x squared, well, when I do the derivative of u with respect to x, du dx, well, that's the same thing as 2x. And so that's what I'm going to replace here in this formula here. And so I'm going to get that this is the cosine of x squared times 2x. And a lot of people like to write this as 2x times the cosine of x squared. Okay? So whenever this is a function of x, instead of just being x, introduce a variable, kind of like doing what we call a u substitution. So I'll let u equals x squared. That way I can write this so that this is a single variable to the first power, right? A single linear variable, the identity variable. So now that I have that, this is a straight application of my fundamental theorem of calculus part 1. The only difference is I have u here instead of x. And so once I do the derivative from my fundamental theorem, my goal is to find dy dx, but y is first written as a function of u, right? And so what I'm going to do is I'm going to do the derivative with respect to with respect to u first, and I need it with respect to x. So I have to multiply that because x squared is inside of that u, right? So remember from the chain rule, you do derivative of the outside function, which is y, and my inside function is u, so I do the derivative of u with respect to x, and that's what I have multiplied here. Once I have that information, I plug it in, and I get my answer. So let's look at this example here, part D. Here I have y equals the integral from 1 plus 3x squared to 4 of 1 over 1 plus e to the t dt. Now, again, we're using our fundamental theorem, so I'm going to go back to the statement of the fundamental theorem, right? When I have something that looks like this, the integral from some value a to x of f of t dt, all right? If that's going to be what my antiderivative or what my definite integral equals is capital F, right? If I want to do the derivative of this thing, it's just going to be the integrand evaluated at x, which is that same variable here, here, and here, right? Well, what I'm going to need to do here is make sure I have an x, a to x. Well, if you look at my function, I have 1 plus 3x squared to 4. So for one, I'm going to have to rewrite this as the negative integral, from 4 to 1 plus 3x squared of 1 over 1 plus e to the t dt. Okay. Now, with that being said, notice this is not just an x here. That is a 1 plus 3x squared, right? So this is what I'm going to replace u. So I'm going to let u equal 1 plus 3x squared. And so I would rewrite y as y equals negative integral from 4 to u of 1 over 1 plus e to the t dt. And now if I want to find dy dx, which is our goal, well, the derivative of y first is going to be with respect to u. And since u is a function of x, because we let u equal 1 plus 3x squared, I'm going to have to multiply that by the chain rule by du dx. That's an x. Okay. Well, dy du is coming from the fundamental theorem part 1, right? So that's going to be that negative that's out front. And that'll be 1 over 1 plus e to the u times du over dx. And this is a du. Okay. Well, since I want this to be with respect to x, I'm going to replace what u equals with respect to x. So I get a negative 1 over 1 plus e to the, well, I let u equal 1 plus x squared. So I'm going to put that here. So that'll be a 1 plus, it's a 3x squared, not just x squared. and that's the exponent on the e. And I do the derivative of u with respect to x. Well, that means the u over dx equals 6x, because I do the derivative of 1 plus 3x squared, which is 6x. So in my derivative dy dx, that's times 6x. And so this equals negative 6x over 1 plus e to the 1 plus 3x squared. All right, and that will be my solution there. All right, let's continue to the fundamental theorem calculus part 2. And this is the one that is, I don't want to say the other one is not as important, but this fundamental theorem is very important because it helps us to actually go around. This really gets us to being able to go around this, doing this limit here in order to calculate areas under curves, okay? And so let's see what it states. Sorry about that. All right, fundamental theorem part 2. It says if f is continuous over the closed interval from a to b, and f is any antiderivative of lowercase f on that interval, then the integral from a to b of f of x dx. Right, okay. So f, lowercase f, is continuous. All right, here we just have x and y. There's no t's. All right, integral from a to b. Our interval is from a to b. So this is a continuous function on the interval a to b, closed interval a to b. F is the antiderivative, right? So if f is the antiderivative of f, then f is like a derivative sitting there, right? So this is almost like having a derivative. Because in order to get the antiderivative, you have to have something that you, because if I take the derivative of the antiderivative, I get back what I started. So f is like a derivative, right? Little f. Capital F is the antiderivative, okay? Remember, this symbol here means we're going to do the integral from a to b, definite integral from a to b, f of x dx, right? This gives us the area under this curve. Now remember, this is a derivative. This is a derivative. Another word for derivative is rate of change. All right, I want you to get what's conceptually happening here. This is a rate of change sitting here. So my y-axis gives us basically rates of change. I'm going to abbreviate that with ROC. My y-axis represents a rate of change. My x-axis is the unit that it's changing by, right? So I'm going to say a unit of change. For instance, if I had a rate of change of miles per hour, and then my x-axis would be in hours because it's changing by hours, okay? Notice when we calculate this area, we're basically multiplying hours by miles per hour, right? So I'll do miles per hour, and I multiply that by hours. Notice they cancel, and I'll end up with miles, okay? So any antiderivative, when you are given the function, right? When I have it in this, all right, so I have my derivative, I'm taking the integral of a derivative, and I obtain my antiderivative, right, which is capital F, it gives the actual total change in the miles over this, whatever function is my antiderivative, all right? So whenever I multiply, I know I'm running out of space here, but what I'm multiplying the length or the width, this will be the height. And this will be like the width, right? My x-axis represents the width, right? And of course, sitting in the background when we do this definite integral is a bunch of rectangles. We let n go to infinity, so we get the actual full area here, right? So we're basically multiplying miles per hour times hour. And what we're going to do is we have this rate of change. We multiply it by change. It gives us total change. Okay? Of a function f whose derivative I am given, all right? This is the given derivative. So if I do the integral of the given derivative, I get the total change in the function whose derivative is given, all right? I know that is kind of tricky and hard to think about. That's why I'm trying to make the point. All right. Well, total change is the total change and not in the derivative function. It's actually the total change in the function whose derivative is given as f. And so if I know the antiderivative, that's the function whose derivative is given, then all I have to do is evaluate that antiderivative at where it ends and subtract from that the antiderivative of the function evaluated at where it begins. For instance, if you want to know how much money you spent, never mind, I was coming up with an example that didn't work, sorry. You want to know how much weight you lost on your diet? Well, you can just subtract to get the total change in weight, or if you gained weight, or if you lost weight, you subtract your ending from your beginning, right? And if it's positive, you get it's a gain or a loss. And if it's negative, it's a gain or a loss, right? Anytime we want change and we have the information from the function, that's what we do. We always do this subtraction. The difference here is that we're given the derivative of that function. And so this integral here says, oh, if I'm given the derivative, if I do the integral of that, it's going to give me the total change as well, right? So what we're going to do is we're going to use this relationship to help us find total change, or help us find the value of the definite integral. So let's look at some examples. Now, these examples aren't conceptual. If you've taken my Math 122 class, we kind of went over this very length with a couple of days of lecture or whatever. This is Math 141, so we don't spend that much time going over it, but I still kind of want you to know what's going on in the background. All right, so let's go to this integral here. The integral from -1 to 1 of x to the 299 dx, right? I want to evaluate this integral. And basically what this says is that this is my little function f of x. And this is going to equal f of b minus capital F of a. And that capital is the antiderivative. Okay? And so what we're going to do first, and I'm going to erase this so I can have some space. No, I won't. Is I'm going to find the antiderivative, okay? Well, the antiderivative, we got to go back to those rules from 4.8. I know it's been a while since we've done that, but go back to those rules, right? This is a power function. When I want to find the antiderivative, we increase the exponent by 1. So I'm going to do 299 plus 1. We know that's 300, so I'm just going to write 300. X to the 300, and we divide by n plus 1, which is also that 300. And what we're going to do is we're going to evaluate that from x equals -1 to x equals 1. And so now that we have our antiderivative, this is capital F of x. That's our antiderivative. We have to evaluate it at our endpoints. And so what we want to do is we want to find f of 1, right? Because our integral always goes from a to b, right? And then we're going to subtract from that what we get when we evaluate it at -1, which is our a. So what I'm going to do on this line above this is I'm going to plug in 1 into our function. I get 1 to the 300th power, 300, minus a -1 to the 300, right? And again, this is our antiderivative evaluated at 1, and this is our antiderivative evaluated at -1. Well, 1 to the 300 is 1, and -1 to 300 is 1. And so we end up getting 0. So this is what this thing right here is, right? What we normally have to do if we didn't go through this process, which we don't want to do, is we would have to do the limit as n approaches infinity of the sum k equals 1 to n f of xk times delta x, right? We'd have to find delta x, which is b minus a over n, 1 minus -1 over n, and then we'd have to figure out what x of k is, right? Well, if we start our interval at -1 and our delta x is basically 2 over n, we're going to add 2 over n each time. So this is going to be -1 plus 2 over n, -1 plus 2 times 2 over n. And so our x of k is going to be -1 plus 2k over n, right? And so we'd have to put this in for x of k. We'd have to put this in for 2 over n, right? Now, this is just xk part. We have to put it into our function, and our function which is given is x to the 99, right? So we end up with this thing to the 299th power. No one's going to do that by hand. We need this integration process using the antiderivative in order to help us get there, because this is nearly impossible to do. No one's going to do that by hand, okay? And so that's what the use of our antiderivatives are in helping us and connecting it to the Riemann sums, the area problem. Let's go to part B. Part B, we have the integral from 0 to power 3 of 4 times cosine of u over sine of u over cosine squared of u du. Now, remember, when we see these, we want to find the antiderivative. Notice this is a pretty complicated problem, right? Remember, we don't have a quotient rule for anti-differentiation like we do when we have differentiation, right? No integration rules for quotient rules, quotients. So what are we going to do here? Okay, well, I've got to figure out what function has this function as its antiderivative. And so what we have to do is we got to get a little, I want to say get smart, but you got to get a little, got to put our thinking caps on. I was stuck. And so what I'm going to do, just because I know how to do this, is I'm going to keep this 4 here. I can't think of an antiderivative sitting here, but I do know that there's a cosine squared, and I know sine over cosine is tangent, right? So I can write this as sine of u over cosine of u times 1 over cosine of u, right? This is when critical thinking becomes important. All right. And now that I see that, I can see that I have a tangent here and the secant, which I know the rule for. We have an anti-differentiation rule for that. So what we're going to do, this is a constant multiplied by my function. I can bring that out front because that's a constant multiple. And this is just tangent of u times secant of u du. And so now that I have that, I got to find out what the antiderivative of secant u tangent u is. And that is secant. So this basically, for secant of u, that is my antiderivative, right? But we have to evaluate it from x equals 0 to x. This is not an x. My input variable is not an x here. It's a u. So I'm going to evaluate that from u equals 0 to u equals pi over 3 by my fundamental theorem of calculus, right? Fundamental theorem of calculus says f of u equals, you evaluate it at b, you evaluate it at a. Okay, so it really doesn't say that this says that this integral here equals this. So this is f of u, but this integral equals this. All right, just like this integral equals that. All right, so I'm going to plug in pi over 3, and I'm plug in 0. Running out of space here. It's getting a little messy. But secant of pi over 3, notice on your unit circle, pi over 3, the secant is 1 over x. Our x value is 1/2. So that's going to be a 4 times 2. And the secant of 0 is 1. So this is going to be a 4 times 1. So that's an 8 minus 4, which equals 4. All right. I'm going to save part C for you to do on your own, and we'll talk about this in class on our next class meeting. So do on your own. All right, let's go to the last page in our notes where we talk about total area. Okay, so we've talked about area and how I'm going to be a little bit particular here. We're going to talk about the area between a function and the x-axis. Okay, so normally area, in general, area is always positive. Okay, it is always a positive quantity. But when working with Riemann sums, remember we were adding terms of the form f of x of k times delta x, right? So f of x of k, that was like the height of the rectangle, and then delta x was like the width, right? And those are multiplied together, right? and we add those terms up, and that represents the area of the under the curve, right? Using those areas of rectangles that we sum up. Okay. Well, when our function f of x of k is positive, right, that means greater than 0, right? Then f of x of k times delta x is also positive, right? Because delta x is always going to be a positive value. Always going to be a positive value because it represents a width. And the way we do it is b minus a. B is always the larger number, right? If I think about my number line, a to b, b is always bigger. If I subtract that, I'm going to get, whether it's positive or negative, I'm always going to, if I do the bigger number minus the smaller number, I'm always going to get a positive value, right? So delta x is always positive. The only thing that can possibly make this expression negative is the functional value. Because if my function f can be above or below the x-axis, right? If it's below the x-axis, then f of x of k is negative, and if it's above, then it's positive. So, of course, when f of x of k is negative, then that product is going to be negative as well. So in case 2, we wouldn't end up with negative area. Uh-oh. Oh, what's going on? All right, we would end up with negative area, which does not make sense literally, okay? Thus, we take the absolute value of the negative area to obtain the correct positive area, okay? And we're going to see this in an example, okay? Let's draw the graph of f of x. All right, we have f of x equals cosine of x. We're going to go from negative pi over 2 to 3 pi over 2. So I'm going to draw me an xy plane. All right, cosine negative pi over 2 is 0. At 0 is 1, and we know it's a sine wave. And this is going to look really messy, sorry, but. So this is a graph of f, right? These two should be sort of symmetric, right? The same congruent shapes, but it looks a little weird, right? So I have my x-axis, I have my y-axis, all right? So what I want to do is I want to calculate the integral from negative pi over 2 to 3 pi over 2 of cosine of x dx, right? So what we said that this is, remember, this is still the limit as n goes to infinity, sum k equals 1 to n, f of x of k times delta x, right? Now, this comes from doing the area of a bunch of rectangles, right? So it's like I'm going to go through and do the area of a bunch of rectangles, right? So on and so forth. And so basically that's going to give me the area, right? But here, when I go to these rectangles here, they're going to be below the x-axis because these are the functional values, and those functional values are the f of xk part, right? Well, we know from the fundamental theorem how to do this. All we have to do is find the antiderivative of cosine, which is sine, right? So this is going to equal sine of x, but we're going to evaluate at x equals negative pi over 2 to x equals 3 pi over 2. Okay, that means I plug in 3 pi over 2 minus, and then I plug in negative pi over 2. Okay, well, sine of 3 pi over 2 is negative 1. And the sine of negative pi over 2, well, negative pi over 2 is the same thing as 3 pi over 2, right? They have the same terminal size. So that is also equal to negative 1. When I subtract two things that are the same, I end up with 0. Remember, this is a Riemann sum. This has to do with area, right? How do we end up with 0, but we can see area there? The reason for that is because with this integral here, doesn't care if my function is above and below. It's going to make everything on above the x-axis positive and everything below the x-axis negative, right? Which is why if we need the total area, all right? So that's what I'm trying to distinguish in this example, going over these concepts here. If we want the total area between a function and the x-axis, and this area involves some negative y values, we have to do the absolute value of the negative area. So I'm going to come back here. my function from from negative pi over 2 to pi over 2, f of x is greater than or equal to 0, right? However, from pi over 2 to 3 pi over 2, f of x is less than or equal to 0, right? So for this area, when I do the definite integral, it's going to make my area seem negative. All right, and so in order for us to get the total area, so we can ask for the integral, which is fine, but if we want the total area, which is what part C is getting at, we're going to have to split this up into two separate indefinite integrals, and then we'll take the absolute value of the one that is negative, right? And so my total area is going to equal, well, it's going to be the integral, it's going to be the definite integral of from negative pi over 2 to pi over 2. Of my function, plus the integral from pi over 2 to 3 pi over 2 of my same function. But here, I'm going to put this one in absolute value. That means when I find the final answer of that one, I'm going to put in the absolute values, okay? Once we do that, we just go through that same process as we did before. We find the antiderivatives, right? The antiderivative of sine of x, cosine of x is sine of x. We're going to evaluate that from negative pi over 2 to pi over 2. And then I'm going to do the absolute value. Antiderivative again is sine of x, but this time we're going to go, all right, let's put some bars here to distinguish this from absolute value. From pi over 2 to 3 pi over 2. And that is in absolute values. And so this is going to equal. Now, this is about to be a lot of stuff that I'm writing, right? So now that I have the antiderivative, I evaluate it at the endpoint. So I'm going to have sine of pi over 2 minus sine of negative pi over 2. Okay? Plus, it's going to be absolute value, sine of 3 pi over 2 minus the sine of pi over 2 in absolute value. And so this is going to be 1 minus negative 1 plus absolute value of negative 1 minus 1. Well, that's subtracting a negative. Those two together make 2. That's a negative 2, but it's in absolute value. That's another 2. And that equals 4. Okay? So the definite integral by itself makes negative areas negative, positive areas positive. So when you calculate this antiderivative, this indefinite integral here, it can cancel out some of the areas. So what you see in this antiderivative isn't the actual total area, right? It makes some of that stuff negative. In order to get the total area, you got to split your integral into two separate integrals, or however many regions or areas that may be above and below. You got to split your integral that way, and then make the areas that are negative, put them in absolute value, and you'll be able to find the total area. All right, and that represents the total change. All right, that's it for this video. See you next time.